off at the quizzes basically. So like all of the reading part is done. We just want to do the quizzes now. So there's going to be like 3 quizzes, and this one, last one, actually has answers, and I don't like that, but I think all 3 have answers. I don't know, but we're just going to write down our own answers and see if they match up correctly. Alright, these have answers. This sucks, but hey, it is what it is. Okay, then that defeats the whole purpose of writing down answers. So let's just go through it, and let's just keep searching stuff whenever we don't like understand anything. This is quiz 1. Not bad. So we just have 18 questions, time limit of 45 minutes. So I'm going to time myself. Currently it's like 7:10. So at 45, it's like 7:55 is when I should stop. Okay, so we have 18 questions, right? This should be easy. So system call executes a transition to kernel mode instruction, then begins to execute arbitrary code with kernel privileges. No, a system call executes the trap handler, right? So this should be false. Okay. It is correct for busy waiting, which is spin locks. So basically like the spin waiting thing that you have to perform better than conventional or traditional blocking synchronization. So that puts the threads to sleep and then wakes them up in some cases. So you already know that when you have like parallel, so when you have like multiple processing capability, so like you have 2 threads which are running at the same time on different processors, right? In that case, it could be like one of the threads asks for an IO operation and another, so one of them is like a consumer, the other one is a producer. So if you have a consumer going first and it spin waits while the processor is still going on, it might be that it's actually better rather than it waiting, because the context switching actually has a bit of an overhead to it. So if it just happens that the time you require for waiting, those few CPU cycles, if you could save them, then it's perfect. So otherwise what would happen is like this guy is going, so the consumer, and it sees that okay, the producer has not produced anything, so it will wait, right? It will wait for the conditional signal, and it will put in the waiting list. So we have to like context switch from that to some other process, right? So it saves us a lot of CPU cycles if the producer is never able, like it's like going to produce it very late or something. So meanwhile the producer is just producing, so it's like it's going on and then it produces something, fine. So it runs in a very nice, short and sweet manner. But by this time the consumer has been switched out into some other process. So that process will have to first run, and then you will once again switch to this thing. So this is bad for both turnaround time. This is bad for the total execution time, since you have to do two context switches extra, where you would instead have to do none if you didn't do this whole stuff. So sometimes it's better to just spin wait. So is it possible for busy waiting to perform better than conventional or traditional blocking synchronization? Yes, it absolutely is. Disabling interrupts to provide synchronization. Alright, so that's like the first technique that we know. This provides only one such lock for the whole machine. Yes, because only one thing can run at a particular time. So you can't do any context switching or whatever. Potentially causing critical events to be missed for the whole machine. So we know that it misses critical sections when there's like multiple CPUs, because you could still have like 2 processes running on different CPUs, and then so 2 threads, and even though the first one has like removed interrupts, the second one is still just going on, right? So it's not like only one thing is going at one time, and like it's not sequential execution exactly. It is in the end a multi-processing thing that you have. So what do you mean? I mean, yeah, sure, they can be missed. What's so it's true apparently. It makes sense, I think. Okay, this question has been regraded. Okay, I don't need to say that. The test and set instruction consists of 2 independent operations. Read the value from memory and replace it with value 1. Not necessarily 1, it's any value that you give it. So it's already false, but it's also not 2 independent operations. It's actually an atomic operation, test and set. So it's false. Question 5, a system call allows a process to execute certain instructions in the kernel's code in user mode. What the heck? No, when you do, you can't execute instructions that are in the kernel's code in user mode, because if you're executing that, you're already in the kernel mode. So what are you talking about? You can never execute something that is part of the OS when you are given control to a user process, because then its address space, it will never leak into the kernel, right? So this is false, I think. Okay, because condition wait releases the condition variable lock in its implementation after the thread is woken up. The thread is explicitly responsible for calling the, so yeah, this is a tricky one. So no condition, so we know that the condition wait just frees the lock momentarily, so it's like it will put it in the ready state for the lock, right? So it will be like once you come back from the condition wait, you once again have to acquire the lock, right? You can't just keep on doing whatever you wanted to do in the code without acquiring the lock, right? Because that would like defeat the whole point of using a conditional variable, so using a mutex, right? So no, the thread is not explicitly responsible. You acquire the lock right away when you, or try to acquire the lock right away when you come out of the condition wait or when you are like signaled. So yeah, so it's false. Yeah, so this is red, it's like this is wrong. The timer interrupt transfers control to the kernel from the user program. Control to the kernel, well, yeah, that's what it's meant to do. Is there anything else? Okay, this is true. Fine. After a multi-threaded process returns from the main, the process will continue running until all threads called pthread exit, assuming no errors. Multi-threaded process, so after it has returned from the, so you call the exit or whatever, the process will continue running until all threads called pthread exit. So this does not happen. The problem with this thing is, so there's a TCB, there's a thread control block for each process. Sure, that's true, but you also have a process control block, and each thread has the same PID in the end. So it's like if you ever context switch and you have a single processor, forget that, you have multiple processors, and if you ever context switch from your current threads, which are like from this particular process to some other process, and this will eventually happen, by the way, right? If you ever do that, then you can never come back, because now the process is like dead, so it's just dead. So like any thread cannot execute. So I'm kind of worried about the space that it would occupy. The you know, the threads are to be removed, right? I guess the thing happens automatically, I'm assuming. So process will continue running until all threads call pthread. So okay, yeah, I don't think so. Not necessarily, right? This may happen, but not necessarily. Performing a system call requires a transfer from user mode to a kernel. Yes, it does. That's kind of the whole idea of a system call. Threads within the same process can share data. Threads within the same, obviously they can share data. They share the RAM, in fact, since they live on the same address space. Okay, but threads in different processes can. So we just saw in the slides a way for them to share data. You can actually have signaling between processes, and thus they can, and you can also use like a file descriptor for doing this, but like that's the heavy way out. So no, threads in different processes can in fact share data. Okay, so this is going to be false. Yeah, that's the correct thing. Fine. Okay, so you're given a code. Okay, so what do you have? You have a global set to 1. This is a void pointer which tells me it's going to be a thread. Yes, it's going to be a thread. So you have void pointer foo, which takes in a bunch of arguments. It prints foo's address. Okay, it prints globals. So global is this variable, this guy's address, which is by the way going to be constant, because like yeah, right. Yeah, I mean the value of the variable, right? So the variable stored somewhere, and this guy's address in the RAM, that thing is a constant as well. So this is going to be a constant. P2 is going to print a constant. P3 is printing the, so I don't know, like, and compiler can just kind of remove this at that point. I guess it does that, but whatever. So P1 is printing address of foo. So foo is this pointer. So that, yeah, there's a bit of a weird thing. So this is one problem I was facing, like in compilers. That forget all of that, because we have to currently focus on the quiz. We are under a time limit, right? So and foo, it's like the address of foo, and arg is the address of arg. Arg is just this void pointer that we have to that we have been given. Fine. So arg is like basically just a value, right? Yeah. So arg is a local variable more or less because it's an argument. So for both the threads, the call stack is like different. So arg is different for both of them, like not the value but the variable itself. So its address is also going to be different. Sure. So P3 prints some different things for different threads. P2 does not. P4 prints the argument itself. So like whatever value you passed in, which I don't know what it is, but okay. And then you also have and foo. So this prints the I don't know. Prints. Wait a second. Foo. Do some lexical scoping stuff. Yeah, I mean this is going to be foo is referencing to this thing which is not in the local scope, so you have to go outside of the scope and it's in the global scope. So in the global scope there's only one foo because you do this before you enter the main class, right? Yeah, so there's only one foo. So and foo is going to be a single constant thing. Although we do not know what it is, it might be just garbage to our eyes, but for the buyer it definitely is not garbage. Alright, so what are you doing? You're doing hmem equal to malloc 1. So heap mem is allocating one space and it's a void pointer. What the heck, but fine. So for I equal to 0 to 3, you do p thread t. So that's a thread. That's how you initialize a thread. Okay, this is the wrong syntax. You use capital P, but fine, whatever. So p thread create. You do use capital P, right? Okay, I guess this is cheating if I search in middle of this. So pthread create PID null, so that's the usual thing. So PID is just the the pthread t thing, right? The thread variable. And yeah, it's passed by reference. Foo is a void pointer, so it's a function pointer, and it's passed by value, right? And then you have hmem, so the heap mem. Okay, so this is the argument, right? So heap mem is the argument, so its address is going to be the same for both of these because it is on the no, the address would be actually the stuff inside, right? Because it's the local variable after it's passed. But the value is the same because so this is the same pointer for both of these. So this arg thing is going to print the same. Yeah, it's going to print the same. Only and arg is a local thing, so it's not going to print the same. And then you have and foo, which is a non-local, so it's going to be the same thing. Global, once again, it's a non-local, so it's going to be the same thing. So P1, P2, P4, all these print the same stuff. So yeah, different threads, fine. So it's just going to be P1, P2, and P4 because this is also a correct answer. Fine. Okay. Then context switching between threads in the same process, which of the following need to be saved and restored between different threads. So we did this. We did context switching, right? Yeah. And what was the whole procedure for a system call? Well, you put stuff in the kernel stack. Okay, no, first the timer interrupt goes off. So then the hardware puts stuff in the kernel stack, and then it gives the control to OS. The OS's first mission is to just get everything from the kernel stack to the process struct. Right, so kernel stack is in the kernel space, and it's like for each thread you have like a kernel stack, if I'm not wrong. Yeah, I think that's how it is, right? Oh, but that is the same question, that why do you need a process struct for this? Oh, because you don't. That's the whole point of a kernel stack, that if you don't want a context switch, you probably don't need it. I see. Yeah, and you also have to put it in the stack pointer, so you need that. Sure. You also have to have some metadata about where everything is, what it's base bound, where is it stored, etc., etc. Yeah. So anyway, the timer interrupt goes off. Boom. Hardware puts everything into the kernel stack. It switches the control to OS, so now you're in the kernel mode. You get everything. You do not actually get everything from kernel stack to process struct because you're not doing a switching right now, right? So you're not doing context switching. Then what do? You just go to the trap handler, right? Since the CPU is like owned by you at this point, so you go to the trap handler. It does whatever it has to do the system call, then you return from the trap, and when you are returning from the trap, you put all of the stuff from the kernel stack into the, so yeah, that's actually run by hardware itself, so you just have to trigger some instruction which does this automatically, like you put everything from the kernel stack. You also have to change the stack pointer, yeah, so that it points to the kernel stack, right? And then you do some weird instruction, I don't know, and it just like puts everything in its place. So it's like it takes everything from the kernel stack and it puts it into the CPU. So now you also have the program counter value which you had initially, and so it's in the correct place now. Yeah, also the base bound values, which is like important, so those are also there, and those are also put in the kernel in the correct place. So once all of that is done, you have basically regained the control, like the user program has regained control, right? In between that you could context switching or anything, but whatever. So with context switching between threads in the same process, oh, you are context switching, which of the following need to be saved and restored? Well, you have to save all the registers, sure. What else is there to save? I mean, it's just a machine state that you have to save. Every one of them has their own stack, sure. Local, no, you don't need to save local, because they stay in the address space. We don't care about that, right? A stack pointer could be anywhere, we don't really care about any of that. Okay, I guess the temporaries, yeah, but like, yeah, I mean, all of that is going to happen automatically because you're saving all the registers in the kernel stack anyway, right? So it's fine. So okay, it's data registers, obviously, stack pointer register, obviously. Buffered data, by the way, is like data which you are going to put into buffers, which is like IO operations. They require these things. Contents of the file, so no, you don't. What file descriptor? There's no thread specific file descriptor. You don't just do that. Buffer data, once again, there's no thread specific buffer data. There is a thread specific machine state, so which has type pointer and data register. So you see all of that. 13th, just libraries. For integers 0 to 3, fork, so it's gonna keep on forking 3 times. It's gonna be like 8 processes in the end. Fine. How do I know this? How do I know it's gonna work? Because so every time you fork, you just copy the machine state and address space and you put it as a different process altogether. So it's as if like the same process is running. It's just that now it has like done one repetition. So it's like I has gone from 0 to 1, and so both of these will be like exact same duplicates of each other, and both of them will like fork again, so they'll duplicate each other. So now it like becomes 4, then it becomes 8, and it just becomes 8 because it's 3, so 3 times, right? Assuming that, okay, so assuming that at least 2 individual calls to the fork succeed, so 2 times, so every time you fork, you basically are creating a process, right? Just remember that. So 2 individual calls, so like in this whole mess of a thing that will happen, 2 of the times the fork call succeeds. All right, what is the minimum number of new processes that may be created? Okay, so it's maybe created in a program. Okay, this is messed up because you're saying minimum and maybe, so maybe is like maximum, but I don't know what's going on, but I'm just going to assume it's the minimum number of processes that we want, and also the new processes. It's not any process, just the new ones. So exactly 2 times, because every time you do a fork, a new process is created. So exactly 2 times, yeah, 2 new processes are going to be created. So that's the correct answer as well. Fine. 2 threads in the same process share. So threads, come on, they share the code and heap. Now I shouldn't say code because it also has some internal like stuff. So it's actually like there's a text section, there's the data, so static data, the BSS thing, all that, uninitialized variables. Okay, so code, data, stack, registers, heap. So 2 threads not share the registers, they have different machine states. This is wrong, like if they would share registers. Stack, they do not share the stack. Both of them have different stack because they're like different function calls, you can think of it like that. Code, yes, they do share code, they do share the heap, and they also share the static data. So this is a bit ambiguous because this data could mean anything. It could also be like local variables, but I'm assuming it means a static data, right? The global data stuff. Okay. What is the content of the program counter when the thread running the following code context switches to C3? Okay, at C3. Assume that the variables are appropriately declared. So okay, so C3 is this command. So okay, first it does a lock, and then it does a wait. We don't really care. It's context switching, right? So when you context switch, you don't care about what locks you have and everything. You just care about like what's the machine state. So if it's context switching at C3, wait, what does that even mean? You have these in, okay, what the heck? So it's wait, condition, and okay, so is this made up of a bunch of instructions, or is it just, if you had to translate this to machine code, so you have a while, so you also have a back jump, like an unconditional jump, and so this is going to be like while some label, and then you have this wait, which is probably an atomic instruction, but it has two of these pointers. I don't know what this is doing. It has to get the pointers, right? It has to get the pointers, so that means it's not atomic, right? It probably just gets them, it puts them into some register, and then it does whatever atomic thing it has to do. Fine, so it's like 3 instructions or 4 instructions, something like that. Okay, and then you probably have a jump back into the label. So you're saying you're at C3, some instruction at C3, I'm assuming, and then you context switch. Okay, so what's the program counter going to be like? Where is it going to point? It could point anywhere. If it's like you're just in the stage of putting your variable, loading them or something like that, then you context switch in that. Yeah, it's okay. These are not necessarily critical sections, are they? Are they? Oh shit! You are inside a critical section itself, aren't you? So if you're gonna switch at C3, you can't switch to anything else which like can do. Okay, but that does not tell you what the machine, because you can still switch. It's just that you can't switch to something which is going to run in the critical section. Sure, but you can still switch, and if you can still switch, then you can switch anywhere, whatever instruction you may be at. So you might just be at the instruction which is loading conditions into the condition value into the like temporaries or whatever. So then it's a messed up thing, isn't it? Because even though like weight is atomic, I'm not sure that getting the values of these variables is atomic. So well, this sucks. We do not know, because we could be anywhere inside of C3, but if you do context switch at C3, where could you end up? Well, you could end up at either at C3, or if you're not at C3 and you context switch, so imagine you have a jump, so you are at the last instruction, and that's where you context switch or something like that. So yeah, wait a second, why are you context switching? Is it a timer interrupt going off, or is it like because you're waiting? Okay, let's assume you're waiting, so you context switch because you're waiting. Okay, so then the next instruction is going to be a jump instruction, right? Because you definitely cannot context switch after you have jumped, but that doesn't make any sense. So it's just before you have jumped, you probably have a context switching thing. So the program counter points to the jump instruction next, which is also a part of this block. So it's like C2 C3 combined is okay. That's not part of any of these things. Okay, but if you had to categorize it, then I guess it best goes into this while construct. We know that this does not translate line by line into the assembly code, but which block does it belong to? If you had to ask that, like which block does a jump instruction belong to? I guess it would be in C2, right? Because it's like the while condition. Okay, then why not C3? Because okay, but because C3 is just, yeah, that condition, so it's fine. So it's gonna be in C2. So you're pointing to some instruction in C2 basically. Cool. You can't context switch the jump obviously. So fine, you are at C2. Okay, what if you are not context switching because of this weight, but I just assume it's because of the weight, because otherwise this is going to be an indeterminate thing. Like you have no idea where it's going to be. So then it's going to be a C2 because you're at a jump instruction basically. The next instruction is on by jump instruction. So yeah, it's C2. Fine. Question 16. So hash includes system, some libraries, we don't care. So for integers I equal to 0 to 3, so once again 3 forks. Assuming that once again the same question, is it duplicate. Okay. Oh, okay, there's a maximum, not a minimum. Fine. So assuming that at least 2 individual calls to fork succeed, what is the maximum number of new processes that may be created in the program shown? Maximum number of new processes. So once again, fork creating process. Okay. At least 2 individual calls to fork succeed. So we know that at least 2 new processes are going to be created. What is the maximum number? Oh, maximum. So that's when you have 8 processes. Sure. Maybe. Yeah, maybe that fits perfectly. This is maximum anyway. So new processes that may be created. That just 8 minus 1, so it's 7. 7 new processes. Okay, that's correct. If one of the threads in the multi-threaded program with n threads calls, okay, a multi-threaded program, n threads, one of the threads calls fork. How many threads are created as? So how does the thread work again? Well, it just has a machine state. It has a machine state, it has its own stack, and that's pretty much all it has. And it has a process ID linked to the process that it's belonging to. So when a thread runs, it's as if the process itself is like running in like a single thread manner. Okay. So if it's going to call fork, it's going to use the process ID of the parent process, right? And it's going to be as if the process just had that one thread running and then it called fork. So it just creates a new process. That's it. That's all it does. And so it gets the variable, but that variable is only being used in that one thread. So every other thread, what is it doing? It does not know the variable, sure, but the process is already created, because the OS is the one who takes care of all these system call things. So yeah, you just created a new process, sure, a new process which has what? Same threads? How many threads? This is a good question. So what happens to the thread control block? Do you copy that as well? Because that's pretty much what defines everything, right? I don't know. I mean, it didn't exactly say that you do that when you do a fork. I'm just gonna assume that you don't. Oh, well, that makes my assumption correct actually. Okay, so you don't. You just have one more thread. Yeah. Okay, this is messed up, but okay, I just have to search this up. Why does this happen? I mean, logically, it seems that it's better if you have all the n threads, right? Okay, but it's just one. Okay, so if like all of the threads call a fork, then you would have a new process every single time. That's bad. Yeah, that's very bad actually. You don't want something like that to happen, do you? Okay. Consider 2 threads, so these 2 threads, executing the instructions as shown. So now they are writing assembly, huh? Okay. Each instruction is atomic. Which of the following values of x, y are not possible if the 2 threads execute simultaneously? Assuming that initially x equal to 1 and y equal to 3. Okay, so it loads into R1x, then it adds 1 to R1, and then it stores into y R1. So it's basically like doing y equal to x plus 1, and this is doing x equal to y plus 1, because it's the same instructions as different variables. Okay. So initially x equal to 1 and y equal to 3, and you're asking which of the following values of x, y are not possible. So we just find which of the are possible, and then that's it, right? Yeah. So okay, this is 6 instructions. They can happen in any sort of order, right? Yeah. Oh, this is gonna be like 6 choose 3 different. Oh, that's bad. What can you do to optimize? Wait a second. Oh, the sub instruction is actually like the sub and add instructions are kind of irrelevant because it could have been any code, it doesn't matter. Only the load store are the ones which we really care about because they are the ones which deal with the main memory, which is the only shared thing that these two threads have. So then it's going to be like 2 choose 2, which is 4 different ways of doing it. Okay. So the first way is like you have sequential, so just two of these are going to be sequential. So it's like if you have x and then this thing, it's like y is x plus 1, fine, so that updates y to 2, and then you have x equal to, oh, it's sub over there, so b is doing x equal to y minus 1, fine. Oh, but then it just undid whatever plus 1 thing we did, so it's just x equal to x, so that would be like x equal to 1 and y equal to x plus 1, so it's going to be like 1 comma 2. That's a possibility. You could also have the exact opposite thing, that this happens first and then this happens later. So then you just have y being the same because it's doing a sub and then an add. But x changes as y minus 1, so it's going to be 2, so it's 1 2. So you have what? Shit, no, it's not 1 2, it's 2 3, sorry. So you have 2 3, you have 1 2. These are the two possibilities. Then you also have, if there's a bit of interlapping, so overlapping or whatever, you know what I'm talking about. So you could have first this load, then this load, and then the two stores. Oh wait, okay, so if both loads occur first and then the stores occur in any order, in fact the loads could happen in any order. I see. Hey, wait, so how many different, oh, that's going to be 2 times, oh, that's 4, huh? And you just have 4 choose 2, which is like 4 times of 3 by 2, so that's going to be 6. We already did the 2 ones, so these are the only limited. Oh, okay, I see. Huh. So all the other 4 ones just have this property that loads happen before stores. Okay, that's pretty nice. So then if loads happen before store, then you just have x and y getting their values. So like, oh shit, but it's all register. Yeah, it doesn't matter because they're different threads, so it's like the virtualization thing takes over. Okay, so then x and y both just get their value into the registers, and then the registers just update the value of the variables. Yeah, so it just becomes like x is y minus 1 and y is x plus 1. So it's like y becomes 2, x becomes 2 as well. So the possibilities are 2 2, 2 3, and 1 2, right? Cool. So which of these are not possible is what you want. So 2 2 is possible, 2 3 is possible, and 1 2 is not here. So the other two are not possible. So okay, 4 4 is just dumb, it's just not going to happen, and 3 2 is also not possible. Right, fine. That's it. That was the first quiz. So yeah, it seems I'm doing it in time. Let's go to quiz 2. So this once again, okay, it has 17 questions, one less than before, and it has 60 minutes to do. Fine, and we're allowed 2 attempts. That's amazing. Alright, so let's do the questions. Semaphores can be initialized to any value in the range negative. So we even saw negative semaphores, didn't we? So yes, this is true. Negative 2 power 31 to 2 power 31. I mean, this is true. They can be initialized. What the heck? What do you mean they can't be? Is there a rule like that? Okay, I don't know. Just move on because we just have 60 minutes, so we just move on. I guess this I'll have to search about. I don't think this is possible. False. You're saying they cannot be initialized in any of these. Okay. Weird. In the memory allocated for a stack segment, if it's completely used up, free memory that is not contiguous. So stack segment is completely used up. Wait, what? Memory allocated for stack segment is okay. Yeah, completely used up. Okay, what does that even mean? Oh, it's talking about segmentation, right? Which we have not started, but I think we have kind of started it somewhat. Fine, so it's all used up, so segment is used. Free memory that is not contiguous with the current stack as allocated memory can be allocated to expand the stack without having to relocate. So yeah, you can change the bound register, that's one thing. So okay, you know, just oh shit, okay, not contiguous. No, you can't do that. You can't because this is not contiguous, so you cannot. Okay, without having to relocate it. Okay, that's just impossible because it's segmentation that you're dealing with. Since you told me it's a segment, so this is false. Right, a process cannot directly read or write into the memory of another process. By memory, I'm assuming you mean RAM. So yes, it cannot directly do that, but it can use signaling. So that's something which is OS going to provide. So this is going to be true, I think. Yeah. Priority donation can. So that's this is something that you see in lottery system, right? Priority donation, that you give your tickets to other people. Okay. So this guarantees that all threads will eventually complete, and the system cannot deadlock. How the heck is scheduling related to deadlocks of all things? No, the system can deadlock. There's nothing about priorities or scheduling or whatever that can change deadlocks. So this is false. All threads will, okay, even that is not guaranteed. The thread could literally just be a while loop, and it will, like an infinite while loop, and it will never complete. And the system can, this is stupid. I mean, this is false, obviously. Different processes may use the same virtual address. Yes, they do use different. Wait, what? Oh yeah, the same version makes sense because you can have two programs, and yeah, sure. But will actually access different physical addresses? Yes, that's true. What's so problematic about this? It's true. First come first serve, FIFO basically. So it's called FCFS as well. Scheduling algorithm has a better average CPU throughput. Okay, as compared to the shortest time remaining first if all the processes do not arrive together. That's a good question. Wait, what? As compared to the shortest time remaining first, not the shortest time remaining first with preemption. Okay, that's, yeah, shortest time if all the processes do not arrive together. So you can't do preemption. Okay. What the heck? If the processes do not average CPU throughput, number of processes completed per no, it okay. So these are going to be the same, in fact. Yeah, because it's the average CPU throughput, right? So the number of processes completed per second. That's fine. Turnaround times are going to be like vastly different based on the kind of processes that you, base of workload that you will have. But yeah, the CPU cycles are exactly the same, in fact, because both of these do not have preemption, so there's no context switching. So they'll just like run one process and then run another one and so on. So they eventually just run like the sum of the CPU cycles in different orders, but yeah, so the average CPU time is the same, in fact. Shortest time remaining first. Wait, shortest time remain. Oh no, okay, shortest time remaining is going to have preemption. Shit. I thought it was shortest time first, which is different. So shortest. Oh, then it's even worse because the shortest time remaining first will have context switches, and at the same time, it also has to run all the CPU cycles that first come first serve runs anyway. So this is actually going to always have a better CPU throughput because guess what? This is doing a lot of context switching. This is never doing context switching more than necessary. It only does one like after the other one has completely ended. So hey, look at that, huh? Yeah. FCFS is actually going to do better than shortest job first with completion, right? With preemption, sorry. In fact, all the time. Yeah, it's true. This is true. Yeah, okay. Why did I see the answer? This is so bad. Fine, just gonna justify why this is true. The signal increments the value of this. So this is AND S, which is I'm assuming a semaphore. It increments the value of the semaphore if no thread is waiting on it. Firstly, it should be a pointer. But okay, this is fine. I'm just gonna assume it's a global variable at this point. Fine, this is okay. Then this is okay. So signal. I still don't know how do you actually do the semaphore thing, like in, you know, the API call for all that. But fine, I'll search it up. So signal increments the value of the semaphore if no thread is waiting. I mean, it increments anyway, whether it's waiting, not waiting, you don't care, it just increments. So okay, but does it increment if no thread is waiting? It does, so it's true. Fine. So if you process in, yeah, okay, if it was like if only if no thread is like waiting on it, then it would be false. If the processes in a system acquire resources in a present or predetermined order, that's like basically a safe state thing. The system can, yes, it can avoid dead loss. That's the whole point of whatever that guy's name is. What the heck is that guy's name? The one who, oh shit, I forgot his name of all things. Whatever, move on. So this is true. Fragmentation. Just need to do something about this happening constantly. Fragmentation may occur in both base and bound and segmentation address. Yes, that's true. In base and bound, you can have fragmentation if you have different sizes for the bound, right? So if it's going to be like that, as you require more space, you increase your bound register, then yeah, there is going to be fragmentation, because like you will have different values for bounds, and then the larger values will find it harder to get space, even though there is a lot of space. It's just like it's not compact. So yeah, fragmentation may occur in base and bounds, and it obviously occurs in segmentation, because I mean it occurs less. The internal fragmentation thing occurs less. It's less wastage, sure. It's more efficient, in fact, right? But so this is a problem of external fragmentation, so you can never avoid that in segmentation as well, right? Yeah. The only way to deal with fragmentation is to have a fixed size for your segments. I'm calling them segments. Really, what I'm getting at is pages, right? So pages have fixed size, and so the only way to deal with it is using pages, which means that you need to have a list of all the different pages that you have, which in itself is a very bad thing, but at least it's better. It's better than giving a huge amount of memory to something, right? Which is what base and bounds does, or still giving a huge amount of memory to something, which is what segmentation does as well. So this is true. In base and bounds address translation technique, a user program can directly modify the base and bound registers. Address translation, you can't do that. Your base and bound are completely randomly determined by the OS. Alright, like it's as if it's a random number generator. That it's not exactly, it's based on the free space, but it's based on a free space list, and the malloc thing, it does a system call, and then the thing. But yeah, for you it's as if it's random. So user program cannot directly modify the base and bound, because if it did, hell would let loose. I mean, there's going to be all sorts of faults, and your computer just is going to do weird things basically. So you cannot do that, right? If instead of 3 segments every virtual address space had 32 segments, okay, that's actually a thing which they used to do, but now they don't. So you used to have like very high number of segments, and they even have the name for that, but I don't remember it. So if it had 32 segments, each of 1 kilobyte, at least it's a fixed amount of space, but whatever. If each of 1 kilobyte, how many bits should a virtual address have? So you have 32 segments, each of 1 kilobyte. So it's like 2 power 5 times 2 power 10. That's like 2 power 15 bytes of. So okay, memory is byte addressable. Cool. Then it's like MIPS basically. I mean, that's the kind of architecture they rely on. So yeah, so you have 2 power 15 bytes, right? And you have 3 segments, in fact. Oh no. Okay, instead of 3 you actually have 32. So okay, so you just have 2 power 15 bytes. How many bits should the virtual address have? Okay, so it's the virtual address, by the way. You do not okay, think about it. Yeah, fine, it's just that thing. Yeah. Okay, so this is a weird question which you know what, I'm not going to tell a story about how compilers figure out like what the virtual addresses are, but yeah, the virtual address just has 15 bits pretty much. Will there be a direction? No, you don't need a direction bit. You can just have simple logic for that. So just 15 bits. Yeah. Okay, which of the following scheduling algorithms will eventually preempt any infinitely looping process? So something with a while true sort of thing. When a process that runs for a finite time arrives. Wait, what? Also, when there's some other process which is also trying to run. Okay, notice that the running times are known prior to the. Okay, that's fine. Whatever. Round robin does that automatically. It's like as long as there are two processes, it will keep on preempting one of them with an interval, right? Shortest time remaining first scheduling will also do that because the first one has an infinite amount of time and the second one actually has finite time, and you already know that the second one has a finite amount of time. So it will just say, oh, that has a short amount of time, so I'm gonna go execute that instead. So it does that. It will eventually preempt this thing. It will instantly preempt this thing, in fact, as soon as this other process arrives, because it knows the runtime. First come first serve, no, because the other process arrived late, so this has to complete, which is well never will, but hey, what does the OS know? Multi-level feedback, that's basically based on round robin, so yeah, it does it. So the following conditions are required for a deadlock. Oh, I'm gonna just tell this by memory because I've just memorized. So you require hold, so like, what was this? Hold and something, what was the thing that you call it? Hold and wait. Yeah, so that's when you yeah, so hold, what the heck was this? Oh yeah, you don't wait when you don't have the lock. So shit, what the heck was this? Yeah, okay, there are only two options for you. Either you hold the lock or you wait for the lock. It cannot be that you're holding the lock and at the same time you're waiting or something like that. And that's completely stupid. So that's one thing. So you have a hold and wait condition. Then you also have mutual exclusion because mutex, come on. And lastly, you also have, you can't preempt the locks, right? So no preemption from the OS's side, because if that happens, then once again all hell breaks loose, because it's sensitive code that you're writing, right? If it's in a critical section, so you don't want to just cut it, basically, like let other things do it, because that defeats the whole purpose of a lock. All right, so that's three things which are required for locks to work. The fourth, which requires a, which makes a deadlock happen, is circular waiting, right? So when one process is waiting for a lock, other process is waiting for other lock, but these processes actually have the locks, it's just in the opposite hands. So then it's a deadlock, right? So there's a circular wait. Yes, threads are holding resources and waiting to acquire new ones. Holding resources and they're waiting to acquire new ones. That's basically what a circular wait is, but fine. Oh, okay, I think this is what hold and wait means. That they're holding resources and they're waiting to acquire new ones. Sure. I see. Okay. Resources cannot be taken away from a thread until, okay, so hold and wait is not that, apparently, which I thought it was. It's actually a condition for deadlock to happen. Sure. Resources cannot be taken away from a thread until it releases them. Taken away from a thread. Oh yeah, that's no preemption. Yeah, that's true. That is required. Every single instance of single instance resource can be held by more than one threads. What the fuck? I mean, the statement itself is wrong, so how is it a requirement? That doesn't make any sense. Who came up with this? This is a factually, like, it's an illogical thing, because a single instance resource cannot be held by multiple threads, right? That's the whole point. It's the whole point of mutual exclusion and some stuff like that, right? So it's just, at an instance you cannot do that. Okay, maybe you are thinking like virtualize that resource or something like that. So no, even that is not allowed because mutual exclusion, right? So this is wrong. This is completely wrong. There are infinite number of resources. There are not infinite number of resources. If that would have happened, you would never run into a deadlock. So you have finite resources. First come first serve is better scheduling technique as compared to round robin when considering the turnaround time and the total CPU throughput stuff, because round robin has a lot of context switching, which we do not like, which, like, CPU cycles, not like so. Average context switching, okay, that kind of works out. I mean, it's true. Starvation, no. First come first serve, as you just saw with the infinite and finite thing, it does lead to starvation of very important processes. In fact, average response time, no, response time is where round robin is going to trump, because it was made for that. In fact, average turnaround time, yeah, that's correct. So why did this guy not choose? I don't know, he must be blind. Let's not do that. Given the following details of processes arriving and executing on a system, all times are in seconds. Show the scheduling order of these processes under round robin schedule, scheduling with a time slice quantum of 2 seconds. Fine. So you just have to do the round robin. That's all you have to do. Okay. You may assume that the time to context switch is, oh, that's a nice assumption. The processes do not wait for the time quantum of the previous process to finish before starting. And that's how it usually goes, but fine. Are added to the head of the queue, and then new processes are added to the head of the queue. New processes are added to the head of the queue. As, oh, okay, so basically new processes are run instantly. In fact, like as soon as you get a new process in a waiting list, we'll just start running that. Right. Oh, that's a bit weird. So like at the time of arrival of a new process, you have to actually do a context switch, which I don't know if that's how it works, but fine. So just, alright, so you have arrival time. Okay, I have to draw something for it, or not. Okay, so the first process arrives at 0, so it's running for 2 seconds. Process 2 arrives at 1, so the time quantum is what, 2 seconds. So this should, I mean, if the process did not arrive, it will just run completely fine. And the second process arrives, so we know that at the time of arrival itself you will context switch, right? Right, at the head of the, oh shit, okay, I get it. A waiting list is basically where you're going to insert it, and it's going to be at the head, sure, but round robin does not care about the order of the waiting linked list. It just cares about what's the next thing, and it just has a circular list sort of thing, which it just keeps going on basically, right? As soon as it reaches the null node, it's like, okay, forget it, I'm just gonna start anew or something like that. So no, it still keeps on executing process 1 apparently, because just adding it at the head is not good enough. You also need it to come into order, right? So yeah. Okay, cool. So process 1 is running, it's running, and it has like 2 seconds of runtime, and process 2 has already arrived, sure, and it requires 5 of runtime. Okay, so it's gonna run for 2 seconds. Now you have 4 seconds done. Okay, and it has 3 seconds left to go. Process 3 is gonna arrive at 4. Okay, so okay, process 3 has already arrived apparently, because so it arrived at 4. You ran for 2 seconds, so it wants to context switch now. And yeah, so the list is going to be like, you're at the last element, and the first element is actually process 3. So you have 3 and 2 in the waiting list. You are at 2 currently when you are trying to context switch. So you are going to go into the next one, but the next is just going to loop back to the head. Even if you had it at the other side, it will still be the same, in fact. So yeah, and even if you think, okay, you added this and now you're gonna like restart and something like that, that's also fine, because it's the first one which will get executed since it's at the head. So process 3 starts to execute, and it runs for 2 seconds more or less. Oh, it just has a runtime of 1, so it just runs for 1 second. Okay, and then once that's done, it just gives it to like whatever the other process is. So at this point 5 seconds has been done. Alright, and process 2 gets the control, and so it's gonna run for 2 more seconds, because once again 3 are remaining. So 2 seconds more, so that's going to be like 7. So 7 seconds have gone, and this was arrived at 6 in fact, so it's already there. So now you have to context switch to this thing, because there are like 2 processes. So you press context switch to 4. So the run, yeah, okay, so the order was like 1, 2 till now. It's 1, 2, and then you do 3, I think. Yeah, you do 3 because it was at 4. So you do 3, it just does completely, and then you go back to 2. So 1, 2, 3, 2, 2 and then it does a 4 and then it does a 2 again. Now 2 only has 1, so it does 2 and then it does 4 again. So it's 1 2 1 2 3 2 4 2 1 2 3 2 4 2, and the correct answer is 1 2 3 2 4 2 4 4 once again. Why? Because it requires 4 seconds, so we just ran it for 2 seconds. But once 2 happens, it just has 1 second, it does that and then it goes back to 4. So it's correct. What they have written is correct. Fine. It's just that I'm doing it mentally, so it's like whatever. Suppose our system contains resources A, B, C. Why do I feel this is going to be that that table thing? It probably is going to be. So we have 17 questions, right? And this is a question. Hey, I think I'm doing good. This is fine. Current system has resources A, B, C. There are 3 processes, 1, 2 and 3, that require some instances of each of these resources to complete. Total available instances of all resources are, okay, there are 3 processes 1, 2, 3 that require some instances of each of these resources to complete. The total available instances are, oh okay, there's a colon, I think I missed that. So it's gonna be fuck, I don't want to see this. Okay, available total. So fine, this is like your total available instances. Fine. And processes are 1, 2, 3. These are resources. Cool. The current allocation of the resources and the maximum amount of resources needed for each process to complete are as follows. So this is the max table, this is the allocation table. So currently it's just 1 1 1, this is whatever. So list of possible execution sequence in the format 1 2 3. Okay, the same as last time. Ensures that the system does not deadlock. So it's the same as those standard things which saw in the slides. Does not deadlock if all the processes request for all the remaining resources. So once again, whatever is the max that you require, you know that either compile time itself. We're just going to give all of it to the process. Fine. Okay. So currently you have how much available? This was total available instance. We don't want that. We wanted the current available instances. So you have already like allocated 3 of each to these 3 things. So it's like it's going to be 5, 6, and 4. So it's 5, 6, 4. Which of these is smaller than 5, 6, 4? Well, this is not. This is also not, and this is also. Wait, what the heck? 5, 6, 4. Oh, okay. It's not just. You also have to account for the allocation, right? So yeah. So this is fine. This is. So it's gonna be doable because okay, this is 1 1 1. So you can take all of that. So it's just becomes 6, 7, and 5. So now it's 6, 7, 5, and this process is like doable. So it does that. Moves on. So it's 6, 7, 5 now. Okay, 6, 7, 5 plus 1 1 1, because it's gonna be like 7. Because every time it's gonna be 1 1 1 in fact. So it's gonna be like 7, 8, 6. So which of this is like smaller than 7, 8, 6? This one not, because it has a 9. This one 5, 3, and then wait, what? Wait, what? 7, 8, 6. Did I do this correctly? I mean, yeah, you are going to get the 1 1 1 thing anyway. So it's just like 2 2 2 gone from each of these. So it's gonna be like 6, 8, should not 6, 7, and 5. Okay, but then you get the 1 1 1 from that. So it's gonna be like 7. So it's just 1 1 gone. So it's like 7, 8, 6. So 7, 8, 6 is what we're looking for. But so okay, 8 does not really matter because it's all low. Then it's 8, 6. But this is 9 and this is 7. So none of these can work. We are doomed, aren't we? Okay, what's the answer? Oh, this is messed up. No sequence possible. That's a new one. I wasn't expecting that actually. But fine, I guess they are. Okay, we were right, I think. How many questions are there? This is the last one. Okay, so given some code, SEMT binary semaphore. You do not, I don't know if you initialize it like this. I don't have any idea. I'll actually have to search up how do you initialize semaphores, but I'm assuming it's SEMT. So it's SEMT binary semaphore and SEMT counting semaphore. Not initialized yet, but these are just semaphores. Fine. You have a thread A, void. Usually you don't use void, you use a void pointer to create a thread, but fine. Okay, so you're passing in the address basically. And why do you have a 0 over there? Thread C. What are threads? What is threads? So it's pthread. Okay, so it's an array of pthread T. Okay, cool. So this is just passing by reference. The heck, wait, what? No, it's not a reference. It's an address, right? It's a pointer. Yeah. Something is going really wrong about, because you're supposed to pass in a function pointer. This is not a function pointer, and you're not supposed to be passing. What the heck is this? Okay, this is messed up. Okay, so you're also passing by pointer the my god, what is this? Fine, I'm assuming this is going to work out somehow. Then you have null, so you're creating these 3 threads and you initialize these semaphores as 0 0. Oh, okay, this is not 0 0, this is the initial value, so it's 2 and 1. Okay, and okay, so it's just 2 and 1. That's how you initialize it. So what do you want? Given the program above, list a possible execution of the threads that will lead to a deadlock without printing anything on the screen. 2 conditions: deadlock, don't print anything on the screen. Fine. Assume that seminit initializes a semaphore. Fine. With a value passed as the third argument. What third argument? Seminit, where is it? Okay, it's this one. Oh, okay, it's just fine. Wait and signal are functions for the wait, semWait, and signal semWait operations of semaphores. Wait and signal, fine. Okay, this is semWait, so waiting semaphore, and semPost, posting. Okay, whatever. Operations of the semaphores. For the solution, list the number shown in red in comments. What? Number shown in red? Everything is red. In comments above in the format 1 2 3. What red are you talking about? Just everything is red. List the line numbers. Okay. So you just, oh, okay, so this is the thing. Oh, okay, fine. In the comments, so you just want to show the line, like what? Possible execution order of the threads that will lead to deadlock. So there's there's context switching, by the way. So this is like what they want is the line numbers basically. Fine, we're not printing anything on the screen. Right, let's try doing it. So currently it's like the values are 2 and 1. So the counting semaphore has 2, this one has 1. So we want an execution order which does not print anything, and which leads to a deadlock. All right. So the first thread does a wait on counting semaphore and a signal on the counting semaphore. Okay. It can never lead to a deadlock because it has to signal on some other semaphore for it to be deadlock, right? Okay, so that's not gonna happen. What about this? You have wait, wait, signal, signal, and here as well you have wait, wait, signal, signal, signal. 3 signals. Okay. I see. Ah, nice. This is going to be, yeah, this is going to be the thing. Fine, 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 fine. So yeah, this is going to be deadlock. So without printing anything. Okay. So like, this is okay. So line 1, your counting semaphore, you will wait. So it like decrements it by 1. So now it's as if it's a binary semaphore. So you basically can treat it like a lock. And this is a classic thing that you have. This is trying to acquire lock 1 and then lock 2, and this is trying to acquire lock 2 and lock 1. So this is, and then it's like signaling. So this will obviously lead to a bunch of problems. This is going to lead to a deadlock. Yeah. So imagine this one does the wait, this one does the wait. So now it's both 0. Oh wait, okay, this is also in the correct order. This is problematic. Why are there 3? Oh, there are 3 waits. That's bizarre. Oh, I can just use this one instead of using A's waiting. Yeah, fine. And then makes sense because it actually has a yeah, so this we want it to be inverted. It's actually here. It's line 10 and 11. Fine. So first you'll just do line 9, so it's 1 down, then line 10. So the binary semaphore is now negative, so it's waiting, and then it cannot execute any further. So then you go to this line 4. So the counting semaphore is now, it's 0, so it's like -1, and so now both are negative, so it doesn't make sense for any other thread to start because it's like all negative. And yeah, we are stuck. It's a deadlock because it cannot proceed further, this cannot proceed further, and there's nothing to, and even this one cannot proceed further, so we really are stuck, aren't we? So the execution and we didn't actually print anything. That's another nice thing. So the execution order is like 9, 10, 4, and that's it. I think 9, 10 and 4, these are the only ones which can execute. So you want to, it's the possible execution of the threads. Yeah, it's going to be 9, 10 and 4 because we want to return the line numbers. Yeah, so it's 9, 10 and 4. Yeah, so it's 9, 10, 4, and then you also have these things 1, 5 and 11, but they never execute. So why would you want to do 1? Okay, so eventually it will, I think. Fine. And then why do they do 5? 5 is which line? It's this line. So it's trying to wait for the binary semaphores. Wait, what? So 9 is there, so it's like 1 down, and 10, its binary semaphore is gone. This is gonna be, did it do the thing correctly or not? You did not get a signal, so you cannot actually go forward. How are you supposed to go to the line 5? It doesn't make any sense. 1, 5, 11. That doesn't make any sense. Yeah, this just does not make any sense. What? So your answer is 9, 10, 4, 1, 5, 11. How are you going to do 1, 5, 11 if you cannot go forward? So you're just like getting all the weights pretty much, right? Dude, you initialized it with 2 and 1. Think. You cannot do this. Like, it's wrong. Right? Like, once it's this 1. Wait a second. Is it wrong? Then you do it for the counting setup. It's like, oh, it's not. Okay, this is fine. They are right. So yeah, you do have to do 9, 10 and then 4. So what that does is it puts everything into 0, 0. So now, yeah, okay. Now once again when you do the wait thing, it's gonna be a problem. And so now you can do 11, 5 or 5, 11 or whatever. But they're also doing 1 over there for some reason, which I don't quite understand, but fine, I guess. That's gonna be a counting semaphore. Okay, I mean that's fine. You can do 5. Just look at it. Let's look at the solution. It's 9, 10, 4, 1, 5, 11. Okay, so first it's 9. Wait, so it's down 1. Okay, then 10. So binary semaphore is down 1. It's 0 now. And so it's 9, 10, 4. So the next one is 4. So the counting semaphore down again. So it's went from 1 to 0. So now everything's like 0, 0. And then what did they do? They did 9, 10, 4, and then it did a 1. Okay, so now counting semaphore is negative and it's waiting at this point. So okay, and then they did 5 and 11. 5 is this statement, binary semaphore. So yeah, okay, counting semaphore was 0 over there, binary semaphore is 0, so it's gonna be going down 1, and now it's waiting. Fine. And then 11 is this counting because this executed, so this one is like capable of execution now. So now it's gonna be negative 1. It's gonna be waiting. Okay, so they are right, actually they are right, and I was kind of wrong. You're right, these do execute, so I have to execute it all the way. Fine. I get it. So the deadlock only happens when everything's waiting. Yeah, it has to hold and it has to wait. Fine. So this was I see, I messed up this one. 17th I messed up, everything else is okay. Fine, let's do the third one. You just have 5 questions. That's weird, and you have no time limit. What the heck? Okay, whatever. Given 3 threads ABC, for which of these synchronization scenarios would you utilize a single semaphore initialized with a value of 2? So it can be decremented 2 times. So you have different options to make sure. Okay, so you have 3 threads. Using synchronization scenarios, we utilize a single semaphore. Make sure the thread B runs after both A and C have completed. Yeah, I mean you could do that. Wait, what? How? Only after it with an initialization value 2. And how would you? Okay, runs after these have completed. You're just going to end up with deadlocks at that. Okay, not deadlocks, but something like that, because this isn't going to work. Even if you hit a bunch of signals, it's just not going to work, is it? Yeah, I mean technically you can, but like, okay, why would you? That's the question, isn't it? One of these would have to give you a thing. Yeah, I mean you're just making your whole life harder, so no, I don't think so. To make sure that, I mean, you can, the whole point is you can actually do it, it's just you probably shouldn't do it. To make sure that only one thread enters the critical section at a time. That's what a mutex is for. So you would initialize it with 1. That's a binary thing, so it's not a good way to initialize it with 2, right? So you would initialize it with, like, you have 2 resources or something to complete thread C before. So you, once again, before, after, these things are problematic. I don't think that's what you use semaphores for. You use conditional variables and these other things for it to prevent more than 2 threads from running. Yeah, that's how you. That's the whole reason that you came up with semaphores, because you want to run 2 threads. Wait, what? More than 2 threads, yeah. So 2 is the limit of resource instances. Suppose that the thread A always runs for 8 seconds at a time and runs forever. Okay, so it runs like 8, then 8, then 8. So it runs for 8 seconds and sleeps for some time. It wakes up, runs for 8 seconds, again sleeps, and so on. In our system, which uses material feedback queue like scheduler, where every process remains in the same queue if it yields before time slice. Okay, if not, it's moved to the. Okay, the following is the structure of the scheduler, where Q2 is So this is round robin, so okay, every queue is just round robin, and you have different time slices, fine. And you have a process A which runs for 8 seconds at a time and it runs forever, fine. So what do you want? A is initially placed at the top queue. It will, so okay, where will it end basically? So first it will like run for 8 seconds and the time slice is 5, so it like not good. So it will be put down right into the 10-second thing, and so now we're just going to run like for 3 seconds and then it gives it up, but that does not actually change anything because it still like stays in that level, and from that point onward it gives up every single time, like because it's going to run for 8 seconds at a time. So it ends up at q1 after its first run. All right, that's cool. So what do you want? Okay, that's just the thing, I think. So it will continue to run on q2. No, it will eventually be placed in q1, after which it will always be placed in q1. Well, yeah. Wait, what? Okay, yeah, I mean this is incorrect. This is the correct answer because it says 8 seconds at a time. It's a time interval, like it's an IO operation, and then it runs forever for 8 seconds, sleeps for sometimes. Come on, people, read the question. Okay, eventually placed on q1, after which it will move between q. There's some messed up stuff. I don't think that's correct. The following Banker's algorithm. That's what I was missing. That's the name which I was missing. Okay, which the following descriptions of Banker's. So it's pretty. I'm just gonna read this. Okay, I basically saw the questions. That's bad. Using Banker's algorithm results in an execution that is guaranteed to avoid deadlock. Yes, that's true. Banker's algorithm can be used to determine whether our system is guaranteed to. I mean, yeah, but you just repeated the same thing as before. So it relies on having known upper limits for resource requested per thread. Yes, this is used in. No, it's not used in recovery. Once you are having a deadlock, you are having a deadlock. Like the only way to recover from it is like to start killing processes. So it's used for avoidance. All right. Yeah, I think that's avoidance, or is it prevention? I think it's prevention. It's likely that you will actually end up with a deadlock. Okay, round robin considering the thread priority for deciding the time slice of a thread. A bit like MLFQ, more specifically the time slice of a thread is equal to its priority. Suppose there's a IO bound. Wait, what? The time slice of the thread is equal to its priority. So if it's a more priority thread, it has a bigger time slice, which is completely opposite to how it usually goes, but fine. Suppose there is an IO bound thread A with a priority of 64 that always runs bursts for 1 second in between IO. Okay, priority 64, so its time slice is also 64, and it always time slice given to it 64, and it always runs for 1 second in between IO. Okay, another CPU bound thread B has priority of 2, so it's basically the opposite. So it's going to be a very weird thing that will have priority of 2 and always runs or bursts for 100 seconds. That's a okay, in between IO. All right, assuming each IO operation takes 1 second and the two threads only leave CPU for IO, what fraction of the time will thread A run on the CPU on average? So this is, you know, it like has 1 second, so it's just like priority 64, but it will just keep on doing the 1 second thing. So it's like if there's no boosting, like there's no priority boosting, then A has a lot more priority, and it like never gives up. So it just always gives up before its time slice is over. So if you're thinking in terms of like a multi-level feedback, you will basically never run B. Yeah, bummer, but you'll basically never run B. Huh. So it will run all the time. Yeah. IO operation takes 1 second. Okay. So okay, we will like run, then IO, run, IO, run, IO, etc, etc. So it seems it's gonna run half the time, 50%. Oh, it's 1/3. Why is it 1/3? Oh, because it's a round robin scheduling. It's not multi-level. Right, so stupid of me. It's round robin, which means it's actually going to be A then B, A then B, and A then B. So when A runs, it runs for 1 second and then it gives up for IO, and then it's like 1 second, and then B runs, it's going to be, so its priority is 2, but it runs for 100 seconds, right? But it still just runs for 2 seconds and it does not give up, but it like, yeah, so you do a context switch basically to A straight up. So which once again just runs for 1 second and then gives for like 1 second IO operation. So it's A IO B, A IO B constantly, because yeah, it's a priority of 2. Wait, so it's like 2 seconds it will run. A will run for 1 second and then it will like give it up, right? So it's with the IO operation. So what fraction of time will thread? Why did you say that the IO operations take 1 second? Okay, this is messed up, because the problem is that when you're making an IO operation, you're first telling the computer that it wants a certain thing to happen, and then you'll just context switch to B, and in the meantime your IO operation will take, okay, because till that whole point is going to be in the waiting list. So if it was like more than that, then you would have to keep on running B with a bunch of context switches, but I'm just gonna assume that context switching takes 0 time. So yeah, this is explainable, fine, in that B will run for 2 seconds, A will run for 1 second. That's the pattern in which they are going to continue. And then yeah, it's 1/3, sure, and all that's because it's round robin. And you'll always get the IO operations result for A just before it starts running. Not just before, but it's like 1 second before, but you get the point, right? It will always be there. And so it will never have to suffer a delay because of that, or another context switch because of that. So it's gonna be like 1/3. Cool, and not cool for me because I messed this up, but move on. Considering the following program pseudocode in which that life, love, and money are semaphores all initialized to 1, okay, and then you have these 3 programs, okay, 3 functions, and then the main function which is doing a thread create, thread create, thread create, ABC and exit. Which of these lines could be printed? So you do a wait signal and then a wait, right? Which of these lines could be? So when you say lines, oh, okay, lines, not output. Okay, so let's see, can this be printed? So you wait for love, and currently it's all 1 1 1, right? Okay, so you decrement it, you signal money, it's 2, you wait for life, you decrement it, and then it prints. So it can be printed, sure. What about this one? So let's start completely fresh because it's threads, so like they can run in any order. So let's just say this one is the one which starts running first, and so it's just waiting life, okay, signals life, and then it waits for love, and yeah, it has all of it, and then it just prints out found love. Similarly over here, it just wait signal, and for different of these, so it's just 2 of these waits which we care about. So all of these can be printed. What's the big deal? No output, nothing is printed. That I don't think that happens, because one of them will eventually print something. Is it possible to get a deadlock? Is it? It doesn't seem like that. Is it possible? wait signal, wait signal, wait. Well, so you can kind of delete these two things, because if you wait for life and you have life and then you signal life, then this whole point of doing this stuff is like pointless. So you can kind of delete this. Similarly, okay, there's no similarly. For everything else you have to do the thing. So you do wait, you signal, and then you wait. Okay, wait money, you wait love, and you signal life. So if these were at 1 1, it would actually make perfect sense, isn't it? All of them are set to 1, isn't it? When it's set to 0, it's actually like and only releases when you have a 0. Okay. Can you get a deadlock? I have no idea. What are the answers? So no output, nothing is printed. That's a correct answer apparently. Oh, okay, it's not a correct answer, it's what they answered. Fine. Finally life, yeah, that's A. Finally life, yeah, that can be printed. B. I found out that can be printed. And wait, what do you mean it can't be printed? Obviously B can be printed, because you just do wait and signal and then wait. Yeah, so what's so problematic about this? It can be printed. What's the big deal about this? Okay, so why is it that, okay, this is just wrong, because obviously B can be printed, so why is it? So I guess it's just incorrect, huh? The question is incorrect, I guess so. So this was good because I had to think a lot. This one really was problematic. This one was okay. This is okay. This one was okay as well. Okay, question 1, question 2 were okay. Question 3 is also fine. Question 4 is where I messed up, like that's on me. And question 5 is messed up itself. So yeah, it's fine. Cool. So all the quiz is done, and I think I have good practice. Next, what I want to do is gate. Just search questions from this thing, and I'm gonna solve that. Let's see if there are any good questions. Or okay, there's another way. What if I figure out where these questions are from, and then I solve exercises from those institutes? It's probably the good idea. Okay, cool. So let's try doing that. I don't really have a mid-sem paper or something like that. This is maybe bad. Abhishek Bichawat. Where did he go to university? Yeah, I know. Move on. And that's weird. IIT Roorkee, Saarland, I don't know, but I guess I know where I want to look for. 2011 operating. This, I know it seems like cheating, but trust me, this is the fastest way. Okay, what is this thing? Department of Computer Science. Oh, this is like all the courses. I don't want that. JAM, no. IIT Roorkee 2001 operating systems course. Mid-sem quiz. This isn't what I want. Oh, okay. This is, what is CSN? Okay, it's operating systems. It's IT Roorkee, and let's see, exclusive notes. What do you mean notes? Curated by Himanshu Kumar. No, I don't want placement preparation. I want not subject code, not this thing. No, I don't want an MSc thing. So let's probably not go to 2017 thing and just do operating system. Let's just do, I think it's Sudoku, right? That's what the site is. Okay, this is advanced. I don't want to do that. Real-time operating system exclusive notes, systems program. This will help in, okay, this will help in academics. Interesting. Methodologies for implementing OS services, file management, some systems program applied with something, whatever. That doesn't look very cool, but fine. Types of, oh come on, I don't want this. Yeah, it doesn't seem like that is going to have a lot of impact. I don't think PhD, like, he probably didn't do it on operating systems, did he? His research experience don't have that, so he probably didn't. Well, he did refer to a Stanford course, so maybe I can just search that. Okay, I think I'll need some time to figure out where to get questions from for like best practice. So yeah, we'll stop for now.